In this video, I'm going to be looking at some past paper style questions based around probability. And this one comes from a mock paper and it's to do with conditional probability. So A and B are two events such that the probability of A is 0.35, the probability of B is 0.46, and the probability of A or B happening is 0.61. So automatically we know that there is a probability of A and B happening together. So these are not independent events. So just to show that, if we have our two events, we know that the probability there of A, this is B, that total probability is 0.35 of that occurring. Probability of B occurring was 0.46, which is all of this area here. So I know that the probability of A or B happening is A union B, that's 0.61. If they were independent events, the probability of A happening or the probability of B happening would both add up to 0.61, but they don't. So what we have is an excess here. So we need to work out what is the probability of that green shaded region in the middle, because in total the probability of A union B is equal to probability of A plus the probability of B minus the probability of A intersection B. That's because we know in this case they're not independent events, so we're going to have the probability of A union B is 0.61. I'm just writing this out in full. Probability of A is 0.35. Probability of B is 0.46. Subtract the probability of A intersection B. When we rearrange that equation, probability of A intersection B, that's A and B, is going to be equal to our 0.46 plus 0.35 minus 0.61. So that's 0.81 minus 0.61 is 0.2. Now, we're asked to find probability of A given B has already occurred. Well, that's the probability of A and B divided by the probability of B, because that is the subset there. So that's going to be equal to 0.2 divided by 0.46, and that is 10/23. That's our probability of A occurring, provided that B has already happened. So just to say, if they were independent events there, A and B, we add the probability of both together, and that will give me the probability of A or B. Okay, but because they're not independent events, we need to subtract this green shaded part here. Okay, so we'll look at another question now. So here we're told that A and B are two events such that the probability of A given B has occurred is a half, and probability of B given A has occurred is 1/3, and the probability of A and B happening is 1/7. Find the probability of A or B happening. So what we're going to end up doing here is writing out what the conditional probability is equal to. So A conditional B is probability of A and B over the probability of B, and that's equal to a half. On this side we have the probability of B given A is equal to the probability of B and A over the probability of A, and that's equal to 1/3. So dealing with the left hand side here, if I multiply both sides by 2 times PB, I have twice the probability of A and B is equal to the probability of B. And on this side, do the same thing, so I cross multiply here. And when I cross multiply here, I have got the probability of A and B. I've just rearranged that there. Intersection B, 3 times the probability of A intersection B is equal to the probability of A. And like I just went through in the last question, as these events are not independent, the probability of A or B happening is going to be the probability of A plus probability of B minus the probability of A intersection B. So we can just plug in the numbers there. A intersection B is 1/7. We have 3 times 1/7 plus 2 times 1/7 minus 1/7, and that gives us our answer, which is going to be 4/7. Okay, we'll look at another question now. So in this question, this is about expected value. A spinning wheel at a carnival is divided into 12 equal segments. Each colour has 3 segments on the wheel. It costs €6 to spin the wheel. Calculate the expected value for playing this game. Is a good value for money? So what we need to do, if you remember, expected value is going to be equal to the value times the probability of getting that event. So we know that at the start, we're told that 12 equal segments, each colour has 3 segments on the wheel. Okay, so we need to work out what the probability of each event happening is. Well, each has 3 segments, and there's a total of 12 colours, so it's going to be 3/12, which is 1/4. So each of those has an equal probability of being a quarter. So if we want to work out what the expected value is, we just multiply the value of getting a red by its probability and adding on the value of getting a yellow by its probability, etc., etc. So it's going to be 1/4 times 0 So total expected value there is going to be €5. Okay, so if it costs €6 to spin the wheel, is it good value? The answer is no, because the expected value of the earnings is €5. If it costs €6 to spin the wheel, then it's probably not worth your while doing it, because you expect to lose money on the game. Okay, so now with this one, we've got a player has 3/5 chance of scoring penalty. During the season, he takes out of 12 penalties. He misses the first 2 penalties. If he misses the first 2, then that's going to be, well, if he scores, it's 3/5. So it's going to be 2/5, which is the chance of failure, times 2, or to the power of 2. And he scores the rest of the penalties. Well, if he scores the rest of the penalties, that's going to be 3/5 to the power of 10. So that probability works out as 9.67 by 10 to the power minus 4, which is 0.000965, because it's 4 significant figures. So that's that probability. Next question, he scores the 6th penalty on the last attempt. So here's where we're going to be bringing in our Bernoulli trial. So he scores the 6th penalty on the 12th attempt. That means he scored 5 of the first 11. So that's going to be 11C5 times the probability of success, which is 3/5 to the power of 5, because he scores 5, times the probability of failure, which is 2/5 to the power of 6, because that's the number of times he fails, and then times the probability that he does score on the last. So overall, that works out as 0.088, and as I said, to 3 decimal places. That's how we leave our answer. This question then is to do with conditional probability. You're told that in a quiz, students are asked to solve 2 puzzles. 45% solve problem 1. 1.25% of the students solve both. What's the probability that a student solved the second problem, given that the student had already solved the first problem? So we're just going to lay out the answer for this. We know that the puzzle 1, the probability of answering the puzzle 1 was 0.45, or 45%. The probability of answering 1 and 2 was 0.25. In this question, you're asked, what is the probability that the student solved the second problem, given that he'd already solved the first problem? So this is probability that he solves the second problem, given that he solved the first problem. So that is going to be the probability of him or her solving both, divided by the probability that that person solved the first, which is going to be 0.25 divided by 0.45 to give you an answer of 5/9. Here, this next question, probability of a water pump being faulty is 0.04. A random sample of 12 pumps is selected off the production line. So we've got a probability there, 12 pumps. Calculate the probability that only 1 pump is faulty. So the pump can either be faulty or not. This is our Bernoulli trial. We're choosing 1 from 12 probability of 1 being faulty is going to be 0.04 to the 1, and the probability of them not being faulty is going to be 0.96 because it's 1 minus 0.04 to the 11, and that gives us an answer of 0.306. It's to 2 decimal places, so 0.31 is the answer for that one. Next one, for the probability of no more than 3 pumps being faulty, well, we then need to just add up either 1 is faulty, or you could have 2 being faulty, or you could have 3 being faulty. You could also actually have none of them being faulty. So you need to work those Bernoulli trial probabilities out and add them together. So it's going to be the probability we had at the start, which is 1, so that was 0.31, that's what we worked out up here, plus the probability of 2, which is 12C2, 0.04 squared times 0.96 to the 10, plus the probability of 3, which is 12C3 times 0.04 cubed times 0.96 to the 9. And I'm just going to change the writing here. And we just need to add on then the probability of none of them being faulty is 12C0 and 0.04 to the 0 and 0 times 0.96 to the power of 12. Just not including the 0.04 to the 0 there because that is the number 1. So that gives us 0.31 plus 0.0702, which gives you 0.0097, and the last one then is plus 0.613. So I've just changed the first figure there not to be 0.31, and when you add up all those figures you have 0.9992, which is 99.9%. So it's highly unlikely that no more than 3 pumps are faulty there. Right, and that's the end of those questions. Keep practicing them. Remember, the ones that come up quite a bit: binomial theorem, conditional probability, and general probability, including relative frequency and expected value.